Good afternoon and welcome to the CERIAS Security Seminar from Purdue University. Our speaker today is Dr. Petros Mouchtaris. He's the Executive Director of R&D for Information Assurance and Security at Telcordia. And his presentation today, he'll be talking about some of the work they do for their government and industry clients.
Okay. Thank you. So what I'm going to do today is talk a little bit about Telcordia. Some of you may not know it. I have a couple of slides on that. And then I'm going to give you a couple of slides of general overview of some of the cybersecurity work we're doing. I just picked a couple of topics that might be of interest. And then I'm going to focus specifically on security for mobile ad hoc networks. So basically, Telcordia is a large company that makes software that runs communications networks. For example, AT&T, Verizon, and so on are big customers of ours. So we have a lot of customers. A lot of innovations in the communications industry has come from Telcordia. So if any of you have used DSL, that was invented by Telcordia. SONET, which is a widely deployed technology, was invented by Telcordia ATM and so on. So what Telcordia does is we basically build large software systems that these companies deploy. Telcordia has over 150 million lines of code that we've developed. One example of the systems we've built is the 800 system. If you ever call an 800 number, that number gets translated into a real telephone number based on where you're calling from, the time of day, the amount of traffic in the network, and so on. And that's not a very complicated network system if you think about it. But what is difficult is one of the requirements is the downtime of the system is very, very small. So it's actually allowed to be down less than 1 minute per year, which means you have to do upgrades in real time, you have to have redundancies and things of that type. So that's pretty much about Telcordia. Within Telcordia, there is my organization, which is called Applied Research. And it's basically a research lab, an industrial research lab. Most of our folks have PhD degrees. We cover a lot of different areas of interest to the company and to the area of communications in general. We, as was mentioned before, we have two sources of funding. Basically, we get funding mostly from government research customers. A lot of times we partner with universities like Purdue and others and get funding from DARPA and other agencies. We also get funding from other customers like communications providers, Verizon, AT&T, and so on, and a lot of the international carriers. And then within applied research, I'm leading the research focusing on cybersecurity. And so, again, a lot of our folks have PhD degrees. Actually, in the area of cybersecurity, a lot of the government-funded research is classified. So a lot of our folks have clearances, including me. And we do a lot of work for some of the customers I mentioned up there. All of the research, the typical research agencies that fund research, are kind of our customers. We don't do a lot of work for NSF because NSF usually funds universities, but pretty much every other research organization we do work with. And then we publish extensively in the research community. So one of the large research areas for my organization is research in malware detection. And today's systems are basically, for those of you that are familiar with that, they're based on signature-based detection. So once they are aware of a piece of malware, today's systems that you may have on your PC, on your laptop, they basically create a signature. And if a software comes in that has the same type of signature, then they detect it that it's malware, and then they block it and they quarantine it and get rid of it. So unfortunately, these systems are becoming less and less effective. So a couple of statistics I have up there. According to some studies, 60% of malware goes undetected by the systems at any point on the web. There was another study by a company called Dambala that said that 15% of malware was still undetected after 180 days. So basically, you have new malware, gets introduced out there, and it doesn't get detected for quite a long time, so it can create a lot of damage in that period. On the left, I have some statistics there that was done by one of the companies. So basically, because today they have found, adversaries have found automated ways of generating malware. So they take a piece of malware, they run it through an engine that spits out basically the same malware in different forms that cannot be caught by the signature. So what companies have had to do is keep generating new signatures. So I heard one statistic by Symantec that builds one of those products, and they say that the number of signatures that generated this year is larger than the signatures that generated over the last 17 years since the product got introduced. So basically what's happening is the attackers are generating all this malware automatically with slightly different signatures, and the signature-based systems cannot detect them. So there's been a research area, and this is kind of more for you to think about. There's been a lot of research in this area in terms of how do you deal with what's called zero-day worms. And that's kind of one of the problems where Telcordia has done a lot of research in. Another big research area is, we call it science of configuration. So configuration management today is done mostly manually. So basically there are a lot of parameters when you set up a router or you set up a host, and people kind of do that. There are some systems that help users do it, but to a very large extent is basically a manual process. So there are various studies that, for example, a study by Yankee Group has said that more than half of the downtimes of IP networks are due to misconfiguration. There was a study done by NSA that found that 80% of vulnerabilities in the Air Force were due to configuration errors. Those are not necessarily network configuration errors. Those might be configuration errors on a host, on a server, so any type of configuration problem. So what Telcordia has done is we've tried to use formal methods for automating this process. So an administrator can, at a high level, using a language that we've developed or any other type of language, kind of define what their requirements are, what they want the network or the enterprise to accomplish. And then we have these tools that automatically go and configure the various devices. And because this methodology is basically automated, there are no configuration errors, and so the downtime of those attacks can be prevented. So in one part of the problem, which is actually just detecting misconfiguration, Telcordia has actually introduced a product. This is kind of an easier problem to solve. So we've developed a product called IP Assure. It's been introduced into the marketplace recently and has won awards for innovation and for actual deployments. Has been deployed by some customers on the commercial side. So that's pretty much kind of the plug about what Telcordia is, what kind of research we do. I just gave you a flavor. I didn't cover all the topics we cover. One of the topics we cover is security for mobile ad hoc networks, so that's kind of what I'm going to focus on today. So I don't know if any of you are familiar with MANET, so I have a slide here to introduce kind of at a high level what the mobile ad hoc network is. So today's commercial networks, if you have a cell phone or a smartphone, those systems are typically have an infrastructure. They have basically those towers. They look like trees, or they're camouflaged if you look outside. And what happens is the cell phone talks to these towers, and then the towers talk to other cell phones, or they communicate to other towers. And that's kind of how communication happens. So any cell phone can actually not talk to another cell phone directly. The way they talk is they go through the tower. And then if you don't have any towers, then you cannot have communications. The situation with laptops is somewhat similar. With laptops, they typically use 802.11, which has what are called access points. Again, that's fixed infrastructure located somewhere, typically in a building or at the airport. And then the laptops talk to the access point, and the access point connects you to the internet or to other laptops, and then you can communicate to each other. Again, without the access points, there's no communication that's possible. Mobile ad hoc networks, the big advantage they have is they don't need any infrastructure. So basically you bring the computers in, and then they talk to each other. And for those of you that are familiar with 802.11, there is a way of using 802.11 that's called ad hoc mode. That's kind of the thing we're talking about. So when my laptop wants to communicate with another laptop, it tries to find a neighbor, and then the neighbor passes on the message to somebody else, and eventually you hope to get to the destination or where you're trying to get to. So key characteristics is each of the node has some routing capabilities. So every node kind of is part of the network, which is different than what happens today. Typically today the PCs don't have routing capability. They just connect through internet to a router, and then the router is the one that has the routing capability. Every node can move, so there are situations where you actually may not have any connectivity because you don't have any other neighbor near you. And then there are no special nodes in general. So every node kind of has similar functionality, and there's no special nodes like a router or a firewall, which you have in an enterprise network. So why are MANETs important? So they have some very interesting applications, and and I'm going to talk about some of those in a couple of minutes. So basically, their advantage is you can bring nodes together. You don't have to set up an infrastructure, build towers, or do anything else. So you bring things together, they create a network, and you're good to go. So there is very little human configuration that's needed. You don't need to change things if things get destroyed. You don't need to kind of set up an access point. You don't need to point the computer to the access point. They also self-heal since there are no access points. So with traditional cellular networks, for example, if there is an earthquake and the tower gets destroyed, or if there is a lightning and the tower gets destroyed, then connectivity around it gets lost. In this case, there's no special node, so it's very easy for them to self-heal, because if a node goes away, then the routing protocol can handle that. So there are specific applications that MANETs are very good for. One of them is communication in the battlefield environment, and the military is very interested in that. When you go into an area, it's a completely new area. You don't have to first go there, bring up big towers, and then be careful so those towers don't get destroyed, and so on. Another one is emergency response, and for example, you go to where an earthquake happened, or where a hurricane went through and all the infrastructure got destroyed, and then you can bring these nodes in and you can set up the network really quickly. Sensor deployments, there was a project called Smart Dust. I don't know if any of you are familiar with. Smart Dust was a project where you had actually thousands of very small sensors, and then having a human try to establish connectivity among all of those nodes is very, very hard. So they used kind of the MANET type of concept for establishing connectivity among those nodes. And then vehicular communications, basically having cars talk to each other, kind of is an application that has been explored. Yes?
Are these MANETs actually used? I mean, these are all theoretically, people have said these are the uses that can be put to, but are people really using them in the real world?
Yeah, there are situations where they're being used. For example, one application has been in actually municipal networks. That's actually the most widely deployed MANETs, or they're also called mesh networks. And there what happened is they wanted to create a network within a municipality, and rather than bringing up towers, they used this capability, so they didn't have to configure anything. They just put a bunch of nodes, and that established a network. On the military side, there is development of real radios that use MANETs. Those have not been deployed widely yet. They're in the experimental stage, but the military is spending billions of dollars actually building those systems. So they're past the research phase. There is a program called JTRS, which is basically, they're called software-defined radios, which is the biggest program that the Department of Defense has for building the next generation of radios, and those are based on these kind of concepts. Okay, so here are some of the challenges with mobile ad hoc networks and whenever you have challenges, that you have very interesting research problems, and that's why MANETs have attracted a lot of research interest. So you have a very unpredictable environment where you have intermittent connectivity, you have a lot of movements, a lot of topology changes. So in terms of doing routing in this domain, it's a challenging problem, and there's been a lot of new routing protocols that have been invented to support MANETs. ITF actually has a working group that has been working in this area for a while. You cannot have special nodes. You have to deal with networks splitting and joining back together, nodes moving in and out of range. You have to make sure you meet the bandwidth constraints that you typically have in a MANET environment. And of course, security for those networks is very interesting. The reason why I got attracted to this research problem is that MANETs, actually, their goal is to make it easy for nodes to come together and communicate with each other. And security is exactly the opposite. So building a secure MANET is kind of an oxymoron, and that's why it has been an interesting research problem. And it has attracted a lot of interest over the last several years. And the other aspect of MANETs is with MANETs, you cannot really have humans configuring those, so the process has to be automated, and that's kind of another interesting research problem. So, as I mentioned, security of MANETs has been an area of interest. I actually also published the first book on the topic. It's kind of an introductory book that talks about a lot of the research that has been done in this area, and it's the first kind of real book. There were some books before that were compilations of research papers. So what I have here is kind of the various research areas that have been done in the past in the area of secure MANETs. So the first aspect that you think about is how do you protect MANETs? How do you protect kind of bad people from getting in? And you usually use the same techniques that you use in traditional security. So cryptography plays a big role. Basically, various encryption techniques and authentication techniques. The things that are different is that you have to have much more efficient protocols because you cannot generate a lot of overhead, which some of these protocols do. You don't want to consume too much CPU because, again, you drain battery, and these nodes typically have limited battery. Another aspect of it that's interesting is key distribution and key management and key revocation. Some of the challenges there is the way usually key management is done is there is a central node that generates this and keeps the certificates, and you cannot have that in MANETs, so you have to have a much more distributed approach for doing key management. And then routing. A lot of the routing protocols for traditional networks don't really have security in mind, and even the ones that were created for MANETs initially really did not look into security at all. So creating secure MANETs or securing the MANET routing protocols that already exist is kind of an area where a lot of work has been done. Other research area of interest is, okay, let's say that somebody has penetrated the cryptographic barriers and is inside the network, or is an insider that is misbehaving. How can you detect the attack? So intrusion detection, which is a typical kind of research problem, it exists already for enterprise networks, and we've leveraged some of that research and applied it to secure MANETs. And actually, this will be the focus of some of the topics I'm going to talk about next. So that's kind of has been the area where I've focused my research, and Telcordia has done a lot of research in. So I'm going to focus in this specific topic. The next area is, once you detect an attack, what do you do about it? So what kind of reaction mechanisms do you use? And policy-based management is one of the area of work that has been done in this area, and Telcordia has also kind of looked into that. And policy management is basically you want to know what to do when there is an attack, but you want to have that be automated. You don't have a human to try to decide what to do. So the way policy management works is you create some rules that say, okay, if this happens, then you should do this, and these have to be quite high level, and then the policy management system will take those high-level rules and try to kind of implement them in real time. And then there's also been a lot of research that has been done to address specific applications of MANETs. So each of those have kind of unique security requirements. So one area is sensor networks, I mentioned before. vehicular networks. And another problem that has been of interest has been secure localization. How can you, if there are various MANET nodes talking to each other, how can you find out where each node is, what's their location, and do that securely? There's been a lot of kind of papers published in this area. Okay, so I'm going to focus next specifically on intrusion detection. I have a couple of slides on how intrusion detection is done today, and what we try to do is basically leverage on that research to kind of advance it and apply it to secure MANETs. So today for enterprises, and I'm sure the Purdue network is kind of protected in a similar way, is there is the internet, you have a firewall between the internet and your network, and then you typically have intrusion detection system deployed within the enterprise to look for intrusions, basically for people that have, for bad things that have penetrated the firewall and are inside the enterprise. So examples of those are host intrusion detection systems. A simple form of them are the Symantec or McAfee antivirus that you run on your computer or your laptop, and there are more general forms of host intrusion detection systems beyond those. And then there are network intrusion detection systems that kind of analyze network traffic inside the network. They usually sit behind the firewall and they try to look for anomalies or malicious traffic. And then very often there is an analysis engine that collects all of the information from all of the different logs of the different intrusion detection systems that the enterprises have, and then they correlate it and they try to find kind of malicious things. And then if you have automated response, then you can implement it also at that point. That's kind of the general approach. And then there's usually three major techniques that are being used for intrusion detection. The top one is called misuse detection, basically also known as signature-based detection. This is the most widely deployed approach for doing intrusion detection. And it's been very successful. I mean, it's even though it has limitations, as I mentioned before, if you see an attack once and you create appropriate rules, then you will stop it from happening again in the future. Again, of course, those techniques do not deal with zero-day attacks, with attacks that are completely new and you've never seen before. The big advantage of signature-based detection, and that's why people like them so much, is they have very small number of false positives. False positives is kind of thinking that something is an attack even though it's not. And the reason why they have very few false positives is because when you specify something as the attack, if the specification is precise enough, then it will be very difficult to find something that's normal that looks like it. Anomaly-based detection is very different. It actually is based on creating typically statistics of what is normal, and then, or some kind of a model. It may not be statistics, it may be some kind of a model of what normal is. And then whatever is not normal, is whatever doesn't look like it, is defined to be an attack. For example, in the case of routing, routers are supposed to send updates of their routes every so often. If they start sending routing updates much more frequently than they typically do, this might be this might be malicious, and an attacker may be doing that just to drain battery from all of the MANET nodes, right? So if you send a lot of routing updates, all of their MANET nodes have to update their routes, and then that drains their battery, and if you do it often enough, all of the nodes will run out of battery. So one way of detecting this attack is you create a statistic of how often routing updates happen, and then if you have updates from a node that are more frequent than that, then you say it's an anomaly, and you kind of detect the attack. Of course, the problem with this approach is that very often it's very hard to have a very good model of what normal is. Because again, with routing updates, in certain cases, MANETs, you need to have routing updates because one node got destroyed or there is a lot of movements, nodes are moving very quickly. So then distinguishing between what's normal and what's kind of not normal, but it happened because something happened, because there was a flood or something got destroyed and so on. So sometimes anomalies may not be necessarily attacks, it may be just something different that's happening. For example, again with routing, the internet, when there is a big event, like a big broadcast, things get overloaded, and that's not necessarily an attack. It's just because that specific day there's something that happened that has generated a lot of traffic. So anomaly-based detection has actually not been widely deployed for exactly that reason. There is a lot of anomalies that get generated, and then the administrators keep running around trying to figure out what's going on, and they waste their time, and at the end there's nothing that happened. Specification-based detection is an even more researchy area. So the idea behind specification-based detection, and that applies a lot to routing protocols, is if you create a precise specification of the protocol, if you have a precise specification of the protocol, then you can create a model, and if the model that you have, if the router that you have is behaving at any point any different than what the specification says, then you can say it's an attack. For example, if the specification says the router should send updates every 3 seconds, whenever you see any deviation from that, then you know there is an attack. So specification-based detection is typically fairly complex, because if the protocol is very complex, then creating the specification in a language that you can use it for doing intrusion detection is very difficult. And in some cases, you may also make mistakes, and then you may end up generating alerts, even though there is not. This is an area of research, so there's been a lot of papers published in this area, but again, not much widely deployed out in the commercial world. A lot of these techniques, again, research has been done for MANETs, for kind of taking them and applying them to solving attacks against MANETs. This slide shows you some of the attacks that might be unique or are unique to MANETs. Again, routing attacks is of a lot of interest. Example of routing attacks is, I mentioned one is overloading a node, trying to drain their battery. Another one is creating a black hole. So, and the idea behind it is I start advertising them that I'm everybody's neighbor, so everybody sends me their traffic, and then I drop all of it, and then no node can communicate with anybody else anymore. You can create a network partition, creating loops. Another attack that has been actually studied a lot in the research literature are packet dropping attacks. In MANETs, for them to work, every node needs to kind of help pass the messages along towards the destination. So there may be nodes that are not cooperating or are pretending to cooperate. So I pass my node to somebody that's closer to where I want to get the message to, and that node says, yeah, okay, I'll pass it along, and they don't pass it along, or they drop it, then routing within the network actually gets affected. So there's been a lot of research in this area. More general denial of service attacks, where again, you can either affect the routing or attack specific nodes. Wormhole attack is an attack of specific interest. I have a couple of slides later on, so I'm going to talk about it in a little bit more detail. And Sybil attack is another attack with a fancy name, but this is a very simple attack where a node takes other nodes' personalities. So I pretend to be Sanjay or somebody else, and I send routing messages, for example, pretending to be somebody else, or even application messages pretending to be somebody else. So Sybil attack is an attack where the node takes multiple personalities. So another special issue with MANETs and wireless networks in general that you need to be concerned when you try to do intrusion detection is what's called promiscuous monitoring. So any of you that may have read papers in this area, that's kind of a thing that a lot of the papers talk about. And so one of the things that makes actually intrusion detection more difficult in wireless networks is your view of reality is not necessarily correct. For example, let's assume that C is a node where you're trying to do intrusion detection. So let's say that D is trying to send a message to A, and it's going through C. So basically C gets the message from D, it passes it to B, and it wants to make sure that node B sends the message to node A. Since C in this example is within the transmission range of B, he should be able to tell whether B sent the message to A or not. In certain situations, for example, if D is doing constant transmissions potentially to other nodes, C may not see B's transmission to A because it may conflict with a D's transmission to somebody else. And so C, actually, his view of what B is doing is not always correct. So B may send the message, but A got it, but because D was sending a message at the same time, it interfered with C's reception, and then C didn't see the message going along. So when you do intrusion detection, especially when you're using anomaly-based detection, it's actually often very hard to figure out what's a real attack versus some artifacts of the way the wireless medium is operating. So here are some of the interesting challenges within the MANETs environments when you try to do intrusion detection, and that has helped motivate some of the research that we have done. So, as I mentioned before, within MANETs, you don't have a fixed infrastructure. So, in the typical enterprise environment that I showed before, you had the network intrusion detection system sitting behind the firewall, and it actually had visibility to all of the network traffic. When you're operating in a MANET environment, you can actually not see all the traffic at any node. So if you only had one node doing intrusion detection, which you can actually do fairly successfully in an enterprise environment, that would not work in a MANET. So the approach you want to have is some approach where it's a distributed approach where you have multiple nodes trying to monitor traffic, and then if the nodes are far apart, then you can actually have relatively good visibility to all the traffic. And there's actually been some research that has said, okay, how many nodes do you need to have in a typical MANET to be able to have visibility over all of the traffic? And of course, it depends on how sparse or how dense the network is. But basically, this challenge really points to a distributed detection approach. Mobility, then again, you have more nodes moving around, and then even if you had good coverage by, 3-4 nodes, if those nodes move around or get destroyed or whatever, then some other nodes need to pick up that functionality, which again points to a distributed approach. You want to have to generate limited bandwidth whenever you do intrusion detection, and so again, you need to come up with an approach that minimizes overhead. Again, you don't want to consume power, too much power, because then you drain the node's battery, and the nodes have limited capability, limited power supply. So you need to come up with an approach for MANETs that minimizes energy use. And then there is a lot of unpredictability, which makes it difficult to differentiate between what's anomalous and what's actually acceptable. So the focus of a lot of the research that we've done is along the lines of creating intrusion detection approach that is cooperative and distributed. So when you think about kind of how can you kind of create such an approach, the first thing that may come to mind is, again, it's a distributed approach. Let's say that everybody is kind of participating, and then if everybody cooperates with each other, then you can actually have good visibility at what's going on within the network and then try to detect the attacks. So one approach is to do it in a completely peer-to-peer basis where everybody is pretty much performing the same type of function, and it acts independently, and it actually, every node can decide, collects data from all of the other nodes, and then it can decide whether there is an attack or not. The positives of this approach is, of course, it's fully distributed. So if any node moves away or gets destroyed or comes in or whatever, this approach still works. And then this approach adapts very, very well to changes. The disadvantage is that if you really want to do good intrusion detection and detect a lot of the attacks, then you need to share a lot of data among all of the different nodes. And then that generates a lot of overhead. And then you also have a lot of redundant activities, because if a lot of nodes are doing the same function, then you're basically wasting a lot of power, a lot of battery on multiple nodes. The approach we focused on is called hierarchical correlation architecture. So it's basically what we do is we give special functionality to each node, and then in a hierarchy that I can actually change and adapt if there are movements and nodes getting destroyed. So the idea behind it is within the neighborhoods, we form what we call clusters, and then those nodes elect somebody to be the cluster head, and the cluster head is responsible for collecting data within the neighborhood and then doing some first cut analysis in that data to try to decide if there are any anomalies. And then the cluster heads of the different clusters, then they go to the next layer up and then share what they have found. So basically they reduce the amount of data they share, and they only share the data that they think are relevant for detecting those attacks. And then as you go up the hierarchy, at the top of the hierarchy, you have pretty good visibility across the whole network, but with a lot less data, so without requiring a lot of redundant data to be sent up the hierarchy. We believe that this architecture uses fewer resources, less overhead, basically it generates less overhead in terms of bandwidth overhead and CPU overhead, because as you go up the hierarchy, data has been reduced, so there is less data to process, so less work to be done, and also fewer nodes are doing this correlation. And it is able to do a better detection because it's possible to share a lot more data than what you do with a completely peer-to-peer approach. The disadvantage, of course, of this approach is it's more prone to Byzantine attacks. Let's say if the root node gets compromised, then a lot of bad things may happen. So the root node may decide that the specific node is bad, even though that node is actually not misbehaving, or the root node can ignore malicious behavior because it's playing this special role. So one of the things that we've looked at is, can you potentially elect multiple nodes to play the role of the root and use some kind of a voting scheme to kind of decide if there is a real attack or detect where there are misbehaviors. So some of that work has been published in the paper I mentioned before. I have down there at the bottom. So one of the, yes please.
In the previous slide, what kind of data is being transmitted from one of the MANET node to another node?
Yeah, actually that's a very good question, and it really depends on the specific application that you have in mind. So I have a couple of potential attacks that we've detected using these techniques, and for example, packet dropping and wormhole attacks. I'm going to talk about that in more detail. But this is a general architecture, so you can actually send any data that you want to send through. So one possibility is to only send alerts of things that look somewhat suspicious at the node level. In other cases, you can send data that you think would be helpful to detect specific type of attacks. So I'll talk about some specific examples later on.
The issue here is about the malicious nodes that want
We can't hear the questions without the mic.
Oh, okay.
Yeah, the issue here is that malicious nodes might want to actively carry out intrusion, and that way they can send incorrect data.
Yeah. So we've looked again. You talk about the Byzantine attack. So this is one Byzantine attack I didn't talk about, but yeah, we've looked into that. So the idea is if you send an alert that's saying I saw this malicious activity by this other node, for example. And one thing you can do is before you take any action, you require confirmation from some other nodes. Again, we can use some kind of a voting scheme to kind of decide, take care of that. One of the big questions is how do you form the hierarchy? So in this previous slide, the nodes, so I showed that you have this hierarchy that's been formed, but the question is how do you elect who's going to be the cluster heads, and how you elect who's going to be the root node, and how you form this clustering architecture. And not only that is, as nodes move away or move around or gets destroyed or run out of power, then you need to be able to kind of change the hierarchy so this hierarchy still operates properly. So one possibility is, there are a lot of algorithms that you can leverage. There is a lot of actually research that has been done on how to do clustering and how to form hierarchies in clustering schemes. So we've leveraged some of those algorithms. The simplest one is a highest degree algorithm where you form a tree to kind of help you do the hierarchy. So this is an area of a lot of kind of research, and I think if you look at the papers, some of the research is there. So one of the applications, and that's kind of the thing I was going to get to, is like how do you apply this to solve a specific real attack? So one of the attacks we looked at is packet dropping attack, and I think I mentioned that attack a little bit earlier. You have a node that is dropping packets. This attack is very easy to detect when a node drops every packet. It's much more difficult to detect when the attacker drops some packets. And it could be a percentage of the packet, it could be packets from specific nodes, it would be packets of specific type, because then it's much more difficult to differentiate between is this an attack, is this because the wireless medium is because there's a lot of loss because of nodes moving around, because of the terrain or whatever. So we've done some research, and the way we detect this attack is each of the nodes sends reports through the hierarchy about the packets that they received and the packets that they sent out. And then what we do is we take these reports and then we correlate them, and we try to decide if there is a node that is actually not forwarding the packets that they were supposed to. For example, if in this specific case, if A is trying to send a packet to B and is supposed to go through X, you can find out through the reports that A and X and B send is if there are any inconsistencies on those reports. If, for example, A sent a packet for B and X said, I did not receive any packets from A, or I received the packets from A and I didn't pass it to B, or I passed it to B, you'll see those inconsistencies. And there is an algorithm that we've developed that can help you detect where the attacker is. In certain cases, of course, to kind of triangulate where the attacker actually is, you need multiple reports from multiple nodes, because in certain cases, for example, X may say, I did send the packets to B, and even though it didn't, and then B said, I did not receive them, you may not be able to tell whether X is lying or whether B is lying. But if you compare those reports among the various nodes, and if the network is dense enough, then you are able to actually find out specifically which node was the attacker. So if you're interested more in that, I have a reference there on the slides for the research was published. The other attack I talked about is called a wormhole attack. And in the case of the wormhole attack, the goal is to create an illusion of a shortcut in the routing. And the reason for doing that is to try and kind of direct a package through a specific node, and that node may have the ability to kind of inspect the nodes or capture them or whatever. So, for example, in this slide, you have the source node 197 try to communicate with node 184, and you have three colluding nodes, 180, 186, and 183 shown in red. And then, so basically, node 180 starts advertising that it's 184's neighbor. So whenever 197 sends packet, rather than going through the real path, which would be through 178, the packets start going through 180. Node 180 actually could not do this tunnel by itself, because if it tried to send the packets to 184, those packets will get back to it, because it will still be the closest node to the destination. So it needs the help of some colluding nodes to get the packets to the actual destination. So what 180 would do is it will pass those packets to 186, and then 186 will pass them to 183, and then 183 will get them to the destination. So basically, the attackers create a path that is malicious, that still get the packets to their destination, but they get through the malicious nodes, and then those nodes can kind of potentially either mess with those packets or inspect them or whatever. So again, the way we've applied the hierarchy to address this specific research problem is one of the things that happens that can help you detect this wormhole attack is that if 180 was really next to 184, So the packets getting to 184 should really have only gone through 2 hops. In reality, they go through 1, 2, 3, 4, 5, 6, 7, 8 hops. So there are ways of, there are things that you can look at to kind of realize that packets are actually have gone more hops than they should. One way of doing it is through delays. You can find out kind of how long did it take for a packet to go from 194 to 184. And kind of that's one way of doing it. The other way of doing it is through bit error rate. Each link usually in a wireless network has a specific bit error rate. So when you have a lot more links, a lot of hops that the packet takes to get to the destination, so the bit error rate should be much higher through those paths. So what we've done is we've created a reports from each of the nodes that the nodes, and again, I think we've done it both with latency and with bit error rate, but latency I think was the one that proved to be the most, the easier to do. So each node kind of sends through the hierarchy the delays that are observing for each packet that they receive, whether this is kind of at the origin, the destination, and all the intermediate paths. And then the route in the hierarchy kind of does this correlation. And again, if you may still have nodes that are lying about how long it took the packets to get there, but if you correlate all of that information, if the network is dense enough, if you get enough reports, and you correlate that, eventually you are able to kind of triangulate each of the attackers and kind of find where the attackers are. This work actually did not get done by Telcordia. This research was done by one of our collaborators at Sparta called Dan Stern, together with Army Research Lab. So this is a paper that I have at the bottom that those two organizations has published. So basically, in summarizing to say, this is research that various folks have contributed. I didn't list all their names because it would be too long to list. But the dynamic hierarchy research that we've done was done together with researchers at UC Davis, Carl Levitt, and various other folks there have contributed. Sparta, various folks there, Dan Stern and others within Telcordia, Rajesh Talpade, Tom Bowen contributed to this research. I'm trying to remember. Army Research Lab funded a lot of the basic research, and some of the researchers actually contributed to the research that we did and are part of the publications. And I think that's pretty much it. So this concludes the presentation. If you have any more questions? Yes?
How do you usually evaluate your work? Is it through
Mike,
theories?
Mike. Okay, maybe I repeat the question. So the question was, how do you evaluate this approach? So I didn't go through much into it. In this specific case, one of the tools that we used has been developed by Navy Research Lab. It's called MANE. I don't even remember what it stands for. It's basically an environment where you can connect. That emulates a wireless network, and you basically give it a scenario that says these nodes are at these locations, and then they start moving around, and it gives it information about the type of radios they have, what kind of connectivity those radios can achieve. And then if you take the model of the wireless network and the mobility scenario that you've put in, kind of where nodes are going to go, and then you can create a fairly realistic kind of environment of the wireless network. And then you kind of implement these technologies, and then that's kind of how we did it. We did the evaluation in actually I think a couple of hundred nodes, and then we generated scenarios that we worked with our partners at Army Research Lab, so they kind of helped us decide what's kind of a realistic scenario, and we ran that through, and then we did the evaluation. A lot of the evaluation was about how the hierarchy performs in terms of how much overhead it generates, because it does generate some overhead, how it adapts, how quickly it adapts, if there are movements, networks being destroyed. In terms of the attacks, those are attacks that we developed ourselves, so we didn't really run any outside kind of red team type of attacks. So we picked some attacks that were well known in the literature, like packet dropping and wormhole attack, and that's kind of how we did the evaluation. Okay. Yes.
Another form of attack that can be related to DNS cache poisoning, because the nodes are not trusted by themselves and there are no special nodes like in the infrastructure we have, like DNS servers which you can trust to a certain extent.
Yeah.
So are there some work related to how such attacks are addressed, or what is the impact of such attacks?
Yeah. So we did not do research specifically on this. We had a program with DARPA actually that looked at how to create servers that actually reliable even if one of the nodes gets compromised. And there are various cryptographic techniques that have actually done similar research for how to give out keys utilizing multiple nodes. It's called threshold cryptography, and there are specific techniques that you can use for creating DNS servers that are actually resilient to one or some subset of the nodes getting compromised and giving out false information. I'm not aware of any intrusion detection work that actually has been done to detect this type of attacks in the MANET environment. Okay. Okay. Any other questions? Okay. Thank you very much.